Now I've already shared the slides. Just a minute. Sorry. Uh, so in the previous class, I have already covered the linear data structure part, the stack and the queue and the linked list. Okay, and I've already mailed you the slides. I hope you have got the slides. And if you still find something, if some topics or something you're not able to understand, you can contact me via mail or via phone. Okay, and today I will start the nonlinear part, nonlinear data structure. And in the nonlinear data structure, we have the tree and the graphs. Okay, so first we will move on to the tree. Now, before going to the tree, there are some basic notations. These are for those students who are new to this subject, data structure. So there are some basic notations of the graph theory. First, we need to see them. Now, see, there these seven graphs are there: A, B, C, D, E, F, and G. See, in the graph, in the figure number A, there are only two vertices, V1 and V2. Okay, and there is no edges between, or no connection, rather, we would say, between V1 and V2. Similarly, in figure B, there are two vertices and there is an edge, and the edge is a directed edge. This is directed from 1 to 2, from vertices number 1, V1 to V2. Now in C, uh, there is also an edge. There are two vertices. There is also an edge from 1 to 2, but there is no direction given. So it is an undirected. In D, see, there are four vertices, and there are five edges: x1, x2, x3, x4, and x5. And some of the edges are directed, some of the edges are undirected. Okay. Now in figure E, you will also find four vertices, and there are five connections, five edges between these four vertices, starting from x1, x2, x3, x4, and x5. And all the edges are directed edges. Okay. Now in figure number F also, there are five vertices, 1, 2, 3, 4, 5, and there are five edges between them, and all the edges are undirected. And one more thing, the vertices number 5 has no connection with all other vertices, all the four vertices, 1, 2, 3, 4, v1, v2, v3, v4, has no connection with the vertices number 5. So v5 is an isolated, you can say it an isolated node, or an isolated vertices. Sorry. And in figure G, you will find there are four vertices, v1, v2, v3, v4, and there are five connections denoted by x1, x2, x3, x4, and x5, and all are directed connections. Okay. Now we have seen the diagrams in the previous slide. Now every diagram actually represents a graph. Okay, this all seven diagrams, seven figures represents the graph. Now what do you mean by graph? in every diagram, you can see there are a set of points, okay, and which are shown by the dotted dots or circles. You may call dots or circles, and they are labeled as either v1, v2, v3, or 1, 2, 3. And apart from the vertices, there are some these vertices, or you may say these points, are actually connected by some lines, or you can say arcs. And every arc is starting from one point and it is ending at another point. Now, how do we define a graph actually? This graph actually it consists of a non-empty set V. This V is called the set of nodes. I told you you may call the set of nodes or set of points or set of vertices of the graph. And there is a set E, which is known as the set of edges or set of lines. And there is a mapping from this set of edges E to the set of pairs of the elements of V. So each edge is connected to some pairs of elements of V, and this is called a graph actually. And we can, if you want to indicate it symbolically, symbol wise, you can write it as G equals to V comma E, where V is the set of nodes or points or vertices, and E is the set of edges. Okay. Now, in the definition of graph, it implies that to every edge of the G, you can associate a pair of nodes of the graph, and X belongs to E is thus associated with the pair of nodes U comma V, where U comma V actually belongs to the set of vertices, and the edge will connect the two vertices U comma V. Now, adjacent node. What do you mean by adjacent nodes? Any two nodes which are connected by an edge in the graph are called adjacent nodes. It may be this adjacent nodes may be directed, may not be directed. Now, directed edge and undirected edge. In the directed edge, an edge will be there which is connected, which will be connecting from one end to another end. This is called a directed edge, while the edge which has no specific direction is called undirected. I told you earlier in the graphs. There are some edges which have direction, and the some edges which do not have any direction. So they are called undirected edge. Now, what do you mean by digraph or directed graph? A graph in which every edge is directed is called a directed graph, or digraph. In short, we can say digraph. In the example, B, E, and G are the directed graphs. You can see B, E, and G, figure number B, E, figure number E, and G. They are all directed graphs. Understood? B, E, and G. They are all directed graphs. All the three. Because there is a directed edge from one vertices to another vertices. Or one node
Sir,
to
does
another.
every vertex needs to be connected, or can there be some unconnected vertices too?
Sorry? Please repeat.
Sir, like, sir, for every vertex, do we need to connect them mandatorily, or can there be unconnected vertices too?
No, it depends upon the problem. There can be some directed edge, or it not some directed edge, depending upon your problem or depending upon your need. If you require to, in some places, in some problems, there is a requirement of some direction from one edge to another. Okay, and in some graph or in some problems where where you are mapping your problem in terms of graph, uh, uh, you may not need some direction. Okay, that depends upon the problem.
Okay, sir. Okay, sir.
And in undirected graph, the every edge is undirected. Every edge is undirected. For example, CNF. Now, what do you mean by mixed graph? In mixed graph, that what I told, that there can, in a graph you can have some of the edges which are directed, which have direction, and some of the edges which do not have direction. It is called a mixed graph. For example, you see figure number D. Just move, go on to the figure number D. Figure number D. See, x1, x2, and x5 are directed edges, and x3 and x4 are undirected ones. So depending upon the problem, you can assign a direction, you cannot assign a direction. So it is called a mixed graph. D is called figure number D is a mixed graph. Okay. Now, what do you mean by loop? Or you can sort, you can also nickname is sling. An edge of a graph which joins the nodes to itself is called a loop. And the direction of a loop is of no significance because you know that it is coming to the same node. It is repeating itself. So no direction is required. Okay. So loop should not have a direction. It is meaningless actually. I think there is a figure. Distinct edges. In case of the directed edges, you can have two possible edges between any pair of nodes which are opposite in direction, that are called distinct edges. And what are parallel edges? Which have certain pairs of nodes which are joined by more than one edges. They are called parallel edges. I think we have a figure. Yes, we have a figure. See, oh, this is again the graphics is not working. See, the in node number two, or in vertices number two, see, there is a loop actually. This loop I am not able to show, but there is a loop. It is not coming in the graphics. There is a loop in node number two. And see the edges from node number two to node number three, there are two possible edges between the two pair of nodes 2 and 3 which are opposite in direction. See, one edge is coming from 2 to 3 and another one is going from 3 to 2 between two pairs of nodes, and so these are distinct edges. Okay, the graphics is not working. I will mail you the slides, you can go in there. And if any graph which contains this kind of parallel edges is called a multigraph. Okay, and if there is no more than one edge between a pair of nodes, then such graph is called a simple graph. Or you may say if there is no parallel edges, so that will be a simple graph. What do you mean a weighted graph? If we assign some weight to the edges of a graph, then it is called a weighted graph. There shall be some values. Okay. And what is an isolated node? A node which is not adjacent to any other node is called an isolated node. See in figure, I have shown you in the first figure. See in figure number F, the node 5 or the vertices number 5, V5 is an isolated node because it is not connected to any, it does not have any adjacent nodes. Okay. And what is a null graph? It is a graph which contains only isolated nodes is called a null graph. That means there is no set of edges. They are just some nodes are there. There are some isolated nodes and there is no connection between those nodes. That is the set of the edges. In other words, you can say that the set of the edges in a null graph is actually empty. It's an empty set because there is no edge. There are only nodes. And uh, for a graph, actually, there is no unique diagram which actually represents the graph. You can represent the graph in many ways. Okay. And some again the figure is not coming. See, on your right hand side, it is a graph actually. Okay, it is a graph. Now, is the two graphs same? Yes or no? What do you think?
Yes, the same.
Yes. But if you look at a glance, if you look it at a glance, if I tell you to just look it at once and see, it may appear that these two graphs are different, right? So that is what I am telling, that there is no unique diagram which represents the graph. You can represent the graph in various ways. Okay, by locating the nodes in different positions, you can vary the graph. So there should not be any unique diagram which represents the graph. There are a number of ways in which you can represent the same graph actually. Okay. And what is the in degree of the node? In degree of the node is the number of edges which have v as their terminal nodes. That the edges which are coming to the v actually is called the in degree of the node v. And what is out degree? Which has v as their initial node. From where? From v, how many number of edges are moving out? That is called the out degree. Okay. মানে যেটা ভার্টিসিস ভি তে ঢুক, সাপোজ একটা ভার্টিসিস ভি আছে আর নোড ভি আছে, ভি তে যতগুলো এজ ঢুকছে সেটা হচ্ছে ইন ডিগ্রি, আর ভি থেকে যতগুলো বেরোচ্ছে দ্যাট ইজ দ্য আউট ডিগ্রি অফ দ্য নোডস। ওকে, অ্যান্ড দি সাম অফ দ্য ইন ডিগ্রি অ্যান্ড আউট ডিগ্রি ইজ কল্ড দ্য total degree of the vertex. Now let us go to the path of the graph. This is a graph actually, and let us consider some path. uh, for the time being, for simplicity, we are just considering uh, node number 2 and node number 4. Okay, the some of the paths from node number 2 to node number 4. Now p1 can be a path from 2 to 4 directly. You can have p2, 2 to 3, and 3 to 4. See, there is a path actually from 2 to 3 and 3 to 4. I am denoting it as p2, this one. Now p3, p3 is a path, suppose, from 2 to 1 and 1 to 4. p4, p4 is a path 2 to 3, again 3 to 1 and 1 to 4. This is p4, suppose. p5, 2 to 3, then 3 to 2, again these are the distinct edges, two parallel, and then 2 to 4. And p6, from 2 to 2, it's a loop actually. What I want to show you in the previous slide, it was not visible. This is a loop from 2 to 2 and from 2 to 4. Okay, so these are, let us consider these paths. There can be many paths also, but let us consider these paths from node number 2 to node number 4. Now let G, suppose denoted by V comma E, be a simple digraph or directed graph. These are all directed graph, such that the terminal node of any edge in the sequence is actually the initial node of the edge. Now what is the length of the path? The number of edges which are appearing in the sequence of the path is called the length of the path actually. Now let us take some example, some definitions, consider some definitions. The simple path, what is simple path or S simple? A path in a digraph in which the edges are distinct is called a simple path. For example, path number P5 and P6. See, path number P5 and P6. Path number P5 is 2 to 3, 3 to 2, and 2 to 4. Again P6, 2 to 2 and 2 to 4. So these are simple paths. Here the edges are distinct. Now elementary path, that is node simple, a path in which all the nodes through which it traverses are distinct. Here in simple path the edges are distinct. In elementary path the nodes are distinct. So it is called elementary path. Examples are P1, P1 to P4. These are all P1 to P4. These are all elementary parts. Here the vertices are unique. And P5 and P6 are simple but not elementary actually. Now what is a cycle or circuit? A path which originates and ends in the same node is called a cycle. For example, 2 comma 2. Okay, 1 to 2 and 2 to 1. So it is returning to the same node. It is starting from the same node and ending in the same node. In C3C example, 2 to 3, 3 to 1, and again back to 1 to 1 to 2. So it's a cycle. And what is a acyclic digraph? In the graph which does not have any cycle is called a acyclic graph, acyclic digraph. Now directed tree. What do you mean by directed tree? A directed tree is a
Sir,
acyclic graph. Yes.
sir, in a circuit, can we go from one node to the same node and then again to the same node two, three times, and it would still be a circuit, or it ends after the first time?
No, if you're returning to the same path, it will be a circle. It's a cycle. Sorry.
Okay, sir. So we can return multiple times to the same point.
Yes, yes, yes. But
Okay.
you cannot have multiple loop in a single node.
Yes, sir. Yes, sir.
That is meaningless actually. Okay, you can suppose in this diagram, suppose in node number 2, there is only one loop, and you're telling that there can be two or three loops or slings for the node number 2, but that is meaningless.
Yes, sir. Yes, sir.
Okay, so what is a directed tree? Directed tree is an acyclic digraph which has one node called it, which is called its root with in degree 0, and all of the nodes having in degree 1, and every tree must have at least one node. An isolated node is also a directed tree. This is an example. See, this is a directed tree. From V0, there are two nodes originating, V1 and V7. From V1, the, there are three nodes, V2, V3, V4. And from V2, you have V5 and V6. Again, from V7, there are two nodes, V8 and V9. And from V9, it is 10, V10. Okay. So see here, each node which has one node actually called its root with in degree 0. See the in degree, what is the in degree of the root? That is v0. V0 is the root. So what is the in degree? In degree is 0. Okay, because no edge is coming to v0, so the in degree is 0, while the other nodes have in degree 1. See, v1, you consider v1, v2, v3, all has in degree 1. At least one edge is coming to v1 or v2 or v3 or v4. Okay, except the root. So this is a directed tree. Understood?
Yes, sir.
Yes. The root has in degree 0. No edge is coming to v0, and whereas all other nodes from v1 to v10, you are at least one edge is coming to the them. So in degree 1. So this is the root node, and this is called the leaf node or terminal node v10, because it does not have any other subnodes. Now let us consider these trees. Now terminal node, I already told you, in a directed tree, any node which has out degree 0 is called terminal node. See, it has out degree 0. Okay, so the terminal node. What is the level of the node? The level of any node is the length of path from the root. It's called the level. In an ordered, what is the ordered tree? In a directed tree, an ordering of the nodes at each level is prescribed. Then such a tree is called an ordered tree. Suppose the diagrams B and C represents the same tree but different ordered tree. See there is a diagram B and C. See, both the trees are same in figure number B and C, but their order is different. And what is a forest? If we delete the root and its edges connecting the nodes at level number 1, we will what will find? We will left with the a set of disjoint tree. And this set of disjoint tree is called a forest. This is a very important terminology and very important question which is asked in your campus interviews. That's what is a forest. What do you mean a forest? If you're asked to explain tree, everyone can explain that. But what is a forest? Very few people know that. So what is a forest? If you delete the root and all the edges which are connecting the roots, you will find a set of disjoint tree. That disjoint tree is called a forest actually. Now there are actually four ways to represent a directed tree. These four ways are Venn diagram, nesting of parentheses, like table content of book, and the label format. Okay, let us see examples. Suppose this is our directed tree. This is an example of a directed tree. Now let us see the first Venn diagram. How to represent a directed tree in terms of Venn diagram. This is our tree, and see V0. From V0, it has two child V1 and V7, right? See, I've drawn two childs V1 and V7. Now, what do you have in V1? V1 has three child actually, V2, V3, V4, three nodes actually. So V2, V3, and V4. Okay. Now again in V2, you have V5 and V6. Clear? Now coming on to the rightmost node V7. In V7 you have V8 and V9. Okay. So V8 and V9. And again in V9 you have V10. So this is how a tree directed tree can be represented as a Venn diagram. You have heard the term Venn diagram in mathematics, right?
So can we denote order in Venn diagram?
Order.
So if there are two same trees but of the different order, so both of their Venn diagram will be the same, right?
Yes, both of the Venn diagrams will be same.
So we cannot represent order in Venn diagram.
No, that order will not represent a Venn diagram.
Okay, sir. Okay, sir.
Now nesting of parentheses. See, we have V0. See at the bottom, I have written V0 and there is a bracket opening closing. In V0 we have V1 and V7. See, V1 and V7. Again, in V1 you have V2, V3, V4, V2, V3, and V4. Again in V7 you have other nodes, two different nodes, V8 and V9. See, oh sorry, in V2 you have V5 and V6, and in V7 you have V8 and V9. Again in V9 you have V10. So this is how a tree can be represented as a nesting of parentheses. Okay. And this is how the third one, like a table content of book. You have seen if in a book, in the first part, there is always a table content, right? 1, 1.1, 1.2, 1.3, then 2, 2.1, 2.3. Similarly, you can represent it a tree also. See, V0, you have V1, V2. Again in V2, you have V5 and V6. Okay. And again in V1, you have, so see the V2 and V3, V2, V3, V4 are at the same level. See, they are at the same level. And again, see, V1 and V7 are at the same level actually. Again, V8 and V9 are at the same level. And V10 is also at the same level of V5 and V6. Right? Just match the levels actually. So this is how you can represent a tree like a table content of book. Now label format. See, one at level 1 it is V0. Again 2 you have V1, and at 2 you have V7. Okay, so this is level 1 V0, and at level 2 you have V1 and V7, right? Now again at level 3 you have 3v2, 3v3, and 3v4, right? 3v2, 3v3, and 3v4. And again 3v8 and 3v9. They are at the same level. Now coming on to the level 4, What is at a level 4? V5 and V6. So 4V5 and 4V6 and 4V10. Clear? So this is how a tree can be represented as a level format. Thank God the graphics is working fine so that I can show you. Okay. Now coming on to the concepts and definitions related to the tree. Now the node that is reachable from a node is called the descendant of a node, and the nodes which are reachable from a node through a single edge are called the children of the node. And what do you mean by M array tree? If in a directed graph the out degree of every node is actually less than or equal to m, then the tree is called an M array tree. And what do you mean by a full or complete M array tree? If the out degree of each and every node is exactly less than or equal to m or 0, and their number of nodes at level I actually will be given by m into I minus 1, then the tree is called a full or complete M array tree. And what is the positional M array tree? If we consider M array trees in which the suppose the m children of any node are assumed to have m distinct positions, and if you're considering that positions into account, the tree will be a positional M array tree. What is the height? Height of the tree is the length of the path from the root to the deepest node. And binary tree, if in a directed tree, the out degree of every node is less than or equal to 2, it is called a binary tree, or you can say BT actually in short form. And what do you mean by strictly binary tree? In strictly binary tree, or you can sometimes say that a two tree or full binary tree, you can also say it. It is a tree in which you every node other than the leaves has two children. Leaf node is actually the terminal node. So other than the terminal nodes, every node will have two children. And you call it as a complete binary tree if the out degree of each and every node is exactly equal to 2 or 0. It should be either 2 or 0. And the number of nodes at level I will be 2 into I minus 1. Then you will call it that tree as a full or complete binary tree. In exam, you have this kind of questions, that what is the difference between a binary tree and a strictly binary tree and a complete binary tree. Okay. So there's much more restrictions. See, this is a binary tree. This is a complete binary tree in which, see, every node has at least two children. Now, what is siblings? Siblings are the nodes that share the same parent node. This is not in your syllabus, positional M array. Now, every tree, you can represent it uniquely by a binary tree. Now, let us see an example. Suppose this is a tree, a directed tree, and you want to convert into a binary tree. You take it A, root node. Then from root node, you have B and F, A to B and B to F. Now there is some rule. I first tell you that rule. The rule is, suppose in as a step 1, you can say that you delete all the branches or all the edges which are originating in every node except the leftmost branch, or except the leftmost. You leave the leftmost edge and you delete all the rightmost edges. Okay. And then we draw edges from one node to the node on the right, which is situated at the same level. That is how it is done. See, from A to B, and you delete the rightmost edge, and that rightmost edge is drawn from B to F. Is it clear, this part?
So could you please repeat once?
Okay. So as a first step, what you have to do, you will delete all the branches or all the edges which are originating in every node except the leftmost. You leave the leftmost edge, and leaving the leftmost, you delete all the edges. And then we draw edges from a node to the node on the right. See, f is on the rightmost, f is the rightmost child. So I delete the edge from a to f, and I draw it from b to f, the horizontal line. Okay.
Yes,
From
sir.
a okay, from a to b. See, since b is the leftmost child, so I draw a vertical edge, and f is the rightmost child, so I draw the edge, directed edge, not from a to f, from the leftmost child to rightmost child. See again, what will happen? C and D. So from B, I will draw a vertical edge, and from C to D, I will draw a horizontal. Clear? Again, E, since from E, I will draw again an edge. I think it is at the leftmost. And now we have G, J, and K. From F, I will draw a vertical line to G, and from G, we will draw a vertical line, sorry, horizontal line, and from J to K, we draw a horizontal line. Again from G, H and I are originating. H and I, we draw a vertical line from G to H and a horizontal line from H to I. Okay. Now represent it like this. See, from A, you are having B. Then from B, see, there are two nodes, C and F. C and F is there. Then from C, you have D, and from D, you have E. Similarly, from F, you have G, and from G, you have H and J, and from H you have I, and from J you have K. This is how you can convert any tree to a binary tree. So this is a binary tree. Okay, this will come in your exam. There are much more examples in the book. You can go through that. Okay, this I just given one example. There are a lot of examples given in the book, and this is how we convert a forest to a binary tree. See, A to G, you draw a horizontal line from A to G. B to C, again from A to B, I will draw a vertical line, and then there will be an edge from B to C. Similarly, from B to D, there will be a horizontal line, vertical line, and from C, there will be a vertical line to E, and from E to F, there will be a horizontal line. Similarly, for G, from G to H, there will be a vertical line. H to I, there will be a horizontal line. Again, from H to J, there will be a vertical line, and J to K, there will be a horizontal line. Again, from I to L, there will be a vertical line. Now, converting this to a binary tree, see, from A, you have two nodes, B and G. From B, you have two nodes, C and D. From C, you have E, and from E, you have F. Just map it. So, in this way, you can convert any forest to a binary tree. Now, coming on to the part 2 of this nonlinear data structure. Now, tree traversal. This is very important from your exam point of view, and also from your campusing point of view, because this tree traversal comes in your campus, not in your campus interviews, in campus exams. So the most common operations performed in the tree structure is that of the traversal, and in this traversal, each node in the tree will be processed exactly once, and there will be a systematic manner. Okay, there are three ways of traversing a binary tree: pre-order traversal, in-order traversal, and post-order traversal. Similarly, what we have done in stack, you remember that pre-order expression, in-order expression, post-order expression. Do you remember that? This is the same thing what we have in
Yes, sir.
binary tree, but the rule is a bit different, because this is a tree, this is a non-linear. Suppose this is our tree. Now the pre-order traversal. What is the rule of the pre-order traversal? First we process the root node. Okay. Then we process the left subtree in pre-order, and then we traverse the right subtree. Okay. So the rule is first the root node, then the left, then right. Okay. You can remember it in shortcut like root node is denoted by n. Suppose n, left is L and right is R. So just remember this three characters N L R for pre-order. First the node, then the left, then the right. So N L R. You will remember it like that. And if any particular subtree is empty, suppose that the node has no left descendant or right descendant, so the traversal will be performed by doing nothing. And if you have a null subtree, it is considered to be fully traversed when it is encountered. Now, what will be the pre-order traversal? Now, first the root node, I tell you. So, what is the root node? A. Then the left subtree. What is the left subtree? B. So, B will be there. Then the left also. The left one is C. So, C will be there. Then we move on to the right subtree. In the right subtree, you will traverse the left first the node like the D. So D is the root node for the right subtree, and again the left one, that is E, then F, and then at last G. Okay, so this is the pre-order traversal. Okay, the node, then the left one, and then the right one. Now the in-order traversal. What is the in-order traversal rule for in-order traversal? First traverse the left subtree, left, then the root node, then the right subtree. Okay, so formula will be L N R. First the left, then the root, then the right. Now what will be the in-order traversal? I told you first the left subtree. So the leftmost subtree is C. So C, then B, then the root node A. So A will be there. Then coming on to the right subtree. In the right subtree, you will first traverse the left subtree, that is E, then F, then again root node. What is the root node of the right subtree? D. So D will be traversed, and then G. Okay, so this is the in-order traversal. Now coming on to the post-order traversal. The rule is the first traverse the left subtree, then the right subtree, and then the root node. So the formula will be L R N. Okay. So what will be the post-order traversal? First the left subtree. So the leftmost subtree is C. So C, E, then again the leftmost subtree, that is F, E, then the right subtree. What is the right subtree? G, and then the root node of the right subtree, that is D, and finally the main root node, which is A. This is the post of the traversal. Now, is it clear? The pre-order, post-order,
Yes, sir.
in-order. Okay, you will be given a tree in your exam, and you need to write the pre-order, in-order, post-order. Okay, and sometimes in the exam, it is even in your campus interviews examination, it also comes that you will be given an in order traversal path. Okay, like C, B, F, E, G, D, A. The in-order traversal path will be given. The post-order traversal path will be given, and you need to draw the tree. That may also come, or the pre-order will be given, and the in-order will be given definitely, either in-order post-order or in-order pre-order. These two order may be given of the tree, and you need to draw the tree. That may also come. Or you this may also come like the in-order traversal is given, the post-order traversal is given. You need to write the pre-order traversal. That may also come. These types of question come in your will be then in a semester exam, and also will be in your campus interview. So practice that. In the books you will find hundreds of example. So just try it out. It is very simple. No, this is not in your syllabus. So you can these are some exercises, and in your home you can try the pre and in and post order traversals for the these trees. Okay. And now how we represent a binary tree as a linked list. Actually, I told you in the linked list, in the double linked list, there will be a data at the between, and there will be a left pointer and there will be a right pointer, lptr and rptr. Okay. And in the middle there will be a data. This is actually a typical node of a binary tree. Suppose this is a tree. So how would you represent a binary tree in terms of linked list? This is the A. From A, now this LPTR will store the address of B, right? Again, this LPTR of B, LPTR node of B will contain the address of C. And since there is no right node, there is no right node of B, so it will contain null, right? Null address. Again, there is no children of C is the actually leaf node. There is no other child. So both the LPTR and RPTR will be null. Okay. Similarly, the RPTR of A will store the address of D, node D, and in the LPTR of D will store the address of E, and the RPTR of D will store the address of F. Sorry, G. Okay. And since there is no left child of E, so the LPTR of E will contain a null pointer, and there is a right child of E which is F, so the RPTR of E will contain the address of F. And since G is the, in case of G is the actually leaf node, there is no other node which is coming out from G. So both the LPTR and RPTR will be null. Clear? This is how a linked list, a binary tree, sorry, is represented by a linked list. And these are the algorithms of the pre-order, in-order, and post-order. Okay, these algorithms are also given in a book. You may sometimes be asked to write these algorithms. Just go through these algorithms. It is actually it is a recursive manner. You know the pre-order definition. First the root node, then the left, then the right. So T is the root node address, and first you check it for the null tree, and just you can go through the pre-order. This is the in-order algorithm. This is also given in a book. The in-order, the formula is first the left child, sorry, left tree, then the root, and then the right tree. And in the post order, first left, then right, and then the root node. Now, this is very important. How can we construct a binary tree from the traversal? I told you there in exam two kinds of traversal will be given, and you need to construct or design a tree, binary tree, from that traversal. Suppose this is an example. The in order and the post order is given. Okay. So there are some steps. You first find the root node, step 1. Okay. How will you find the root node? In the pre-order, if the pre-order traversal is given, the first node will be the root node. That is a trick. And in the post order, the last node will be the root node if the post order is given. Okay. and then find the right subtree and left subtree. Okay, if the pre-order is given, I told you in order will be given, definitely in order will be there, but in, in addition to in order, either sometimes post order is given or pre-order is given. So if pre-order is given, then the first node will be the root node, and if post order is given, then last node will be the root node. Okay, and if you find the root node once, see in this example on the left hand side, a is the root node, post order is given, so the last node will be the root node. So a is the root node. If you find the root node a, now go to the in order. Since you find it a, where is the a? Here is the a. So the left part of a will be the left subtree, the right part will be the right subtree. This is how you divide that. In step 2, find the left and right subtree, right? And Inorder Traversal will give you the left and right subtree. Once you know the root node from pre-order or post-order, you find that root node in the Inorder Traversal, and you can divide the left subtree and the right subtree. See an example. This is the post-order. This is the Inorder. Okay, A is the root node. Okay, I told you. So here is the A. You find it A in the pre-order Inorder, and the left part of the A will be the left subtree, and the right part of the A will be the right subtree. So let us go step by step. You need to write an exam in this way, actually. Design the exam in this way. From A and B, see, the left node is DGB, what I've told you, and the right is HEICF. Clear? Now we can again break it. From A, you have B. Since B is adjacent to A, and you have D and G. Again from A, you have C. Since C is adjacent to A in the post order. Okay, so C is the rightmost tree. HEI and CF. Then again from B, you have D and G. D will be the left one, because in order, I told you first the left node will be there, and D is at the first in order. So D will be the left one, and G will be the right one from D. Okay. Similarly, from C, sorry, in case of the HEI, you see after A, H is there in order. So HEI, so after what is the in order? First the left, then root, then right. Okay, so H and I will be the left and right, and E will be the root node. See, H and I will be the left and right subtree, and E will be the root node. This is how you construct a binary tree. You need to show it step by step, like what I have shown in this slide. You cannot design do it in the rough column and just draw it a binary tree, because there is marks for the individual steps. Okay.
So could you repeat once again about the step marking?
Step marking is there. If in order is post order traversal is given, this comes in, if in a semester exam, this will come of at least 4 to 5 marks. So you cannot directly design a construct. You do all the rough work. I saw in the answer scripts that some people do, they do it actually. I'm not telling it, they do it honestly, but they do all the things in the rough work and just design a tree, and they hope that 5 marks will be full, 5 marks or 4 marks will be given. But that is not the case. You need to show it step by step, what I have shown you. From A, DGB, HEIF, then again the second step, from A, B and C are divided, then from B, D and G. In this way you have to show it step by step. Then you will get full marks for your semester exam. But in your campus interview, you need to do it just at once. Right? That's what I'm trying to tell.
Okay, sir. So we have to show the steps, so and then design the tree, right?
Then design a tree. Step what I have shown in the slides, one by one. See, I'm showing it E, from E to H and I. You need to show it step by step. Then you will get full marks actually. Otherwise, you will say that,
Okay,
sir, I have designed a tree. It is correct. Why I have given 3 marks out of 5? So you need to show the steps actually. Okay, but in a campus interview, you need to write it just once. But in the exam, you need to show it how you are constructing your tree. Okay. Again, the pre-order in order is given. See, now this is from pre-order in order. Previous example was from post-order in order were given. In this example, I will show you pre-order in order. So what I have told you, in pre-order, the first node will be the root node. So which is the first node? G. G is the root node. ওকে, ইন অর্ডার গিয়ে খুঁজলাম জি কোথায়, জিটা এখানে। এবার জি এ দ্য লেফট পার্ট উইল বি দ্য লেফট সাবট্রি অ্যান্ড জি এ রাইট পার্ট উইল বি দ্য রাইট সাবট্রি, left subtree, right subtree. Okay, now just start drawing. G in the left sub part will be the QBK CFA and the right sub part will be PED HR. Okay, now again further decomposing it, from G you have B. Why B? देखो pre order, after in pre order what is the rule? G sorry G root, then left, then right, so B will be left, that is why B is at the left, next left, then B, then again Q, and from it will be, what will be left? KCFA. So KCFA will be on the right side. Now again from G, P will be on the left, P will be on the right side. Why? See, after in order, after G, the first node is P.
So could you please explain from first once again, sir, this example?
Okay, this is clear. The left part is
Yes, sir. Yes, sir.
QBK CFA and the right part is PEDHR. Then from G, see, I took B. Why B? See, in pre-order after G, the first node is B. So what is the formula for pre-order? Root, left and right. So root is G, then that comes B, so B will be there. Okay, then again Q is there, so left part will be Q, and then again the remaining part ACK will be on the right side, KCFA, sorry. Okay, and again from G you see that there is P is there, because in order C, after G the next node is P, and what is the formula for in order? Left, root and right, so P will be on the right hand side, the rightmost side. Then EDHR, again from Q, sorry, from B, A will be on the rightmost tree, and from A, KCF will be on the left. See the order of, in the in order the KCF is there. Similarly, in the pre-order CKF is there. So it is grouped, and the A is different. So A is given on the rightmost side. Now just check it. The pre-order, in the pre-order BQA. So what is the formula for pre-order? Root, left and right. See, root is B, left is Q, A is right. Is it clear? So this is correct. You can backtrack it actually. After drawing it, if you feel that I have done something wrong, you just backtrack it with the pre-order. Similarly, in the P, the rightmost part will be D. Okay, why? And then the leftmost part will be HR. See, in the diagram, in the in order, see P is the rightmost. Then see the in order for this tree. What is the in order? E, D, and HR. See the in order E, D, and HR. E will be the left node, D is the root, and HR is the rightmost node. Is it correct? So my design is correct. You can backtrack and check it. Now finally, from A, C will be there, and K and F is there, and just check it with the pre-order. In the pre-order, what is the rule? First root node, that means C, then K, then F. Right? Just see in the pre-order, C, K, and F is there in the same sequence. So my design is correct. And and from the HR, R, and then H. Just check it in the in order. What is in the in order? Left, root, and right. See, P, E, E, D. Left is E, root is D, and H is at the right, leftmost H, and the rightmost is R. So it is matching with our Inorder traversal. If you are confused that whether my tree is correct or not, when you design the tree, when you have constructed the binary tree, just match it with the in order and pre-order, whether it is matching or not. You can just backtrack and check it. This is the easiest way to check whether your BT is binary tree is correct or not. Okay, you can backtrack and check it. This is how we also do, because if there are five or six uh, characters, then it is okay. If it is more than 5 or 6 characters, you can get puzzle sometimes, like in this pre-order and in order. So you can just back calculate it and just check it. This is the trick actually. Okay, now coming on to the linked representation of the binary tree. Now in the binary tree, this was our linked list representation of the binary tree. And what we do, oh, I told you. Now there are some in the threaded binary tree. The vested null links actually in the binary tree can be replaced by thread. Which are the vested null? See, there are some vested null from in B also, node number B. In node C, there are two vested null pointers. So we can represent it. This null links we can represent it by threads. So a binary tree is threaded according to the particular traversal order. The threads for the Inorder traversal are the pointer to the higher nodes. And what is the rule? If the left link of the node P is null, suppose, then that link is replaced by the address of its predecessor. And if the right link of the node P is null, then this link is represented by the address of its successor. And because the left or right link can denote either a link or a thread, we must somehow able to distinguish them. So how will you distinguish them? We will represent the thread by a negative address, or we can give a flag to the leftmost or rightmost pointers to check that. See, data is there, LPTR, RPTR is there, and there is a leftmost thread, L thread, and there is a rightmost thread, R thread. So L thread is true. It denotes it's a thread link, and if it is false, then it's a structural link that it contains the address. And similarly, the R thread, if it is true, it represents a right threaded link, and if it is false, it will represent the structural link actually. And there is a head node is there, which serves as the predecessor and the successor of the first and last three nodes. So there will be a head node. Apart from the root node, there will be a head node on the top, which will contain the address of the first node and the last node, terminal node. See an example, and it will be clear. Suppose this is the Inorder traversal, CBAEFDG. Okay, so we can design a threaded binary tree for this. How? See, from B to A. B to A link is there. So we give an arrow from B to A. Then from C to B. Then again from E to A. Okay. Then from F to E. Then from F to D. And then from D to D. This is how you can represent a threaded binary tree. There is a head node which will contain the address of, the left will contain the address of C, and the right will contain the address of G. See? Right must contain the address of G. By this, what will happen? The in-order traversal will be easier. You can know that from which node I have to go to which node. This is the fully in-threaded binary tree. See, C to B is there. Then from D to A, then from F to G, sorry, E to G, then the head node will contain H and it will contain the H. And what are the advantages of this threaded binary tree? The in-order traversal is actually faster than the unthreaded version, as there is no stack required. You don't have to design a stack for the in-order traversal. Okay, you can just by seeing the thread which connection is there, you can use it. And it also determines the predecessor and successor for the in-order traversal. And a stack is required actually to provide the upward pointing information in a binary tree, which actually threading provides without stack. If you are using a threaded binary tree, you don't need a stack for keeping this in-order traversal. Okay, because you are having a upward pointing information, which node is pointing to which node. By that you can check the in-order traversal. And it is also possible to generate the successor or predecessor of any node without having the overhead of stack. And what are the disadvantages? The threaded trees are unable to share common subtrees. You cannot share common top subtrees, and if negative addresses is not permitted in programming language, then 2 additional fields are required. And insertion and deletion are more time consuming. Traversal is easier, but insertion and deletion will be time consuming, because you have to adjust the threaded and structured link. If one node is deleted, you need to adjust the threaded link or structural link. Now the binary search tree, should I go this binary search tree, or I will teach it in the next class?
The next class, sir.
Next class, okay. Now just keep it up to here. Now let me take the attendance. I think only 9 people are there. Roll number 49 is there. Roll number 49.
The roll number 49 was present.
Yes, I saw him. I saw him. Right.
Yes.
I saw him. 61 is present.
Yes, sir, I'm present, sir.
85 is present. 95 is present. Roll number 2 of lateral 2.
Yes, sir, present.
Lateral 3, lateral 4, lateral 6.
Yes, sir, present.
Any more apart from this? And
Sir,
lateral 7.
sir.
7, sorry. Lateral 7 is there. 1, 2, 3,
Sir, lateral 3 achi.
7. 9 students are there. 9 students are there. Is it 9? Okay. So the next class will be on Friday. That is on
Yes, sir, Friday.
11th from 10 to 12. 10 to 12. Okay, no problem.
Okay, sir. Okay. No problem.
Okay, so I will set the meeting ID and will mail you. And
Yes, sir.
after completing this part, the tree and the graph part, I will mail you the slides. Okay.
Okay, sir.
Thank you.
Thank you.
Thank you,
Attend
sir.
the class.
Sir, thank you.
Okay.